It's great to be here. I would like to thank my good friend, Henry Tai, and the organizing committees for inviting me here. And today, I'd like to talk about a subject, quantum computing. It's very much in the news, both in the scientific community and also even the popular press. And even though quantum computing, the concept, has been around for 20 years, but to many people, even among computer scientists, it still seems to be a mystery how quantum computer could derive so much computing power. And many people would ask, is this just a fad? Is this something that's going to pass? And today, I would like to introduce the basic ideas and give an in-depth introduction to quantum computing. And hopefully, it will explain why many people find the idea so exciting. And I'm going to claim that quantum computing actually is not a fad. It is not going to go away. And in fact, I am going to try to make the case for quantum computing actually is a great science, like many of the great sciences before. And so we are really witnessing a historical period. And I think that we don't have enough time to start out from the logical beginning, namely to define what great sciences are. So I'm going to try to persuade you by example. Let's look at some of the indisputable great sciences in the past. And the first example I want to present is X-ray crystallography. Namely, you shine the X-ray through some structure, and from the results, you'll be able to figure out the structure of the material. It all began in 1894 when Röntgen discovered X-ray. And there's some mysterious object having some effect. And so it's called X-ray for unknown. And it's a great discovery, and in 1901, Röntgen was awarded the first Nobel Prize in physics. In 1912, Van Looy confronted the question whether X-ray is a wave or a particle, because those were the only two possibilities for people in those days. And he confirmed it actually is a wave. And he demonstrated that by putting this unknown substance onto some structures, you will create something like a diffraction pattern, just like the ordinary wave. And so it is critical that you use the right substance to be the target crystals, so that the atomic spacing between them is of the right magnitude, so that that it will be able to show a diffraction pattern. And because X-ray has such short wavelength, if you use the usual setup, the optical setup, you will not see the diffraction pattern. In 1913, the Bragg's father and son pair, they derived a mathematical formula for diffractive pattern, so that it actually, now you can use it in reverse, so that if you shine the X-ray through a crystal and you're looking at the diffraction pattern structure, you will be able to deduce what the structure of the crystal must be. And so this shows that X-ray is not just a new discovery of a new kind of matter, but it actually enables you to explore a region of science which previously people would not be able to access. In the 1920s, progressively people use it to determine structures of metals and inorganic molecules. And then later on, people get really ambitious, and for very large biological molecules, in the 1937 to 1954 period, Hodgkin were able to deduce such structures. And in 1950s, Perus and Kendall derived the structure of the myoglobin structure, which is the molecule which enables people to breathe. And of course, perhaps the most well-known of them all, Crick, Watson, Wilkin, and Franklin, they deciphered the DNA for humans, so that we now know that the secret for the design of living beings actually, at least for us, look like a double helix. And all these names that I mentioned, all these events, they were awarded with the Nobel Prize, either in chemistry or in physics. And from the 1960s even to the present day, the X-ray crystallography is still the main weapon for attacking structures of molecules. Although there are now competitors in the horizon, but they are still, by now, still the main subject. So therefore, with so many Nobel Prizes, I think that there's no dispute. X-ray crystallography is a great science. The second example I would like to present will be heartwarming for my computer science colleagues. I would claim that computer science is also a great science. In 1928, David Hilbert, arguably the greatest mathematician of last century, presented a talk and in which he discussed the question that is it possible that all mathematical theorems can be proved by some type of mechanical procedures? Namely that if I want to know a theorem is true or not, then it's something which many people fear. And is it possible we can mechanize it so that I can just run my computer program for it, and it will turn out, it will say that, yes, the theorem is true, or the theorem is, give a proof of it. And now, this is an interesting question which led to many ramifications, actually very important, including the famous logicians Kurt Gödel about some really, really nasty aspect of human reasoning. But we are going to focus on the really positive. In 1936, Turing invented a Turing machine model. Exactly, it was in response to Hilbert's question. And the point is that Hilbert left unspecified what he meant by a mechanical procedure. So in other words, people had no formal definition, no rigorous definition what a computation is, what a computer is. And Turing changed that. He not only gave a definition of a computation, but also he invented a machine, a Turing machine. It's a little bit clumsy, but extremely simple. And it actually is the forefather of all the supercomputers of today. The architecture from a mathematician's eyes, they are sort of indistinguishable. And now Turing and his colleagues in the 1930s thus actually gave everybody thought is a satisfactory answer to what a computer should look like, what a computer would do. They thought they had found the ultimate definition of a computer. Now, of course, this is a very important, even though it was a kind of paper machine, and because the development of electronics and later transistors enables us build the really fast computers like today that become indispensable in every sphere of human activities. And von Neumann and others have designed the computer carefully, and Shockley, Bardeen, and Breton invented transistors, which really they got a Nobel Prize also, and make the spread of computers more or less inevitable. And in the 1960s to the present day, of course, as they would say, the rest is history, and we all are very familiar with the enormous influence the computers have in our lives. And I think that we can also conclude that computer science is a great science. And from this, we can derive some characteristic that great science often happens when you have new ideas. It involves the intersection of the scientific discipline, and most of all, it involves a disruptive technology that enables new explorations previously unimaginable. The X-ray crystallography is a new technology that is disruptive. Previously, we cannot touch. We have no idea how to analyze the material, its basic constituents. And computers enable us to do long-range weather prediction and many other things, which previously just you cannot imagine that if you have all the human beings working on the weather prediction problems and hope to get an accurate prediction for 10 days from now, I don't think we can do it with human powers. And now I'm going to make the case for quantum computing in that it has the characteristic that I just mentioned. But actually, better than that, I'm going to argue that quantum computing literally is a result of the interaction between physics, quantum physics, X-ray crystallography, and computer science. So you're going to see how I mean. So in some sense, it's really the child of X-ray crystallography and computer science. So I think that in my Chinese mind, having a great lineage also helps in arguing for the case. So now I'm going to give you an in-depth introduction to quantum computing. And I think that you will not be able to get deeper than that. I think that's the whole secret of quantum computing, why it is so powerful, is contained in here. It involves a particular disruptive computing paradigm, but it involves a leap in imagination. So previously, we have a crystal, and we shine X-ray through it, and from the pattern, from the effect, we deduce about some properties of the crystal. And I would like to ask you to imagine that suppose I have a computational problem. I have a function f, and I have an input x. And I want to know what f of x is. So that's the information. And I would argue that let's just imagine f and x. Just imagine it to be some type of crystal. So in essence, let's just imagine that we grow a crystal with structures that is based upon the description of f and x. And now we are going to throw a particular wave at it. I'm going to explain how the wave will look like. And then let's observe its diffractive pattern. And then you're going to see some bright spot, you're going to see some dark spot. And actually, by analyzing where the bright spots are, it's going to tell you the secret of what we want to do. Namely, that if you do it carefully and if you're lucky, then you will be able to construct the answer f of x. So that's the story that we would like to go on. And now, we'll see that the crystal that we grow could be very, very large. So if the input has n bits, say 100 bits, the size of the crystal that we imagine, it's going to be huge. The size, to describe it, the size, if you want to implement it, the crystal would look like something like 2 to the 100. So it's going to be an exponential size crystal. However, now, here is where the physicist's contribution ends and where the computer scientist's contribution starts. That in computers, we are very used to use software sometimes to do simulation. And in particular, the design of jumbo jet planes. And nowadays, using the software simulation is often cheaper and more accurate than the wind tunnel and the hardware devices. And now, the quantum software simulation we're going to see, it is qualitatively even better than the simulation of things like the design of a jet. It actually involves, it's able to do the simulation of the effect of putting a wave through the crystal, do this experiment with a logarithmically size in terms of the actual size. So this will shrink the exponential size down into the feasible range. But this can be done only if you have a quantum computer. The simulation, it has to be a quantum simulation. And perhaps even now, let me tell you what are the two technical points. The first one is that okay. The first one is the difference is following. So let me make the point here, that in the X-ray diffraction, we don't do anything special. You just have a normal strength X-ray, and you see the diffraction pattern. What we are going to do, as we are going to see, is that we are going to imagine that the strength of X-ray becomes weaker and weaker. It becomes so dim at the end. It's only one photon at a time. We'll do this diffractive experiment, and we look at where the photon would end. That would be enough for us. We don't need to see the entire big picture, just like the X-ray photographs you have when you go to the doctor. We are just interested in experiments where one photon is doing the diffraction, and we look at it. So that's the first thing that we do that. And that actually is also the trick why we can exponentially slow down. Because if you want to simulate it, you want the whole picture, then you have no other way. Just knowing all the data takes the exponential side. But if you're only interested in performing one experiment, then it turns out quantum computer, in the favorable cases, can do the simulation of one photon diffraction with an exponential speed up. Okay, so you're going to see how this will come about. Okay. Let me illustrate with a seemingly toy problem. It's Simon's problem, and he gave a quantum solution to it in the same paper. Let's imagine the following problem. You have a black box, and now this black box, what it can do is to input an n-bit string, and then it output an n-bit string. And now, it is not one-to-one, namely that given an output, you may not be able to identify exactly which input that enables you to get to this output. But it actually is a 2-to-1 mapping. So for every possible output pattern, so there are 2 to the n possible n-bit strings, and 1/2 is 2 to the n minus 1 of them are possible outputs. And for each one of these output, there are exactly 2 input strings that can map it into this output. So it's a 2-to-1 mapping. Okay. And in fact, this is not just any black box. This black box has a secret S. S is itself an n-bit string. And the 2 input, which are mapped into the same output, they are related by the relation. One of them is x, then the other is x plus s, where the plus is bitwise modulo 2 addition. Okay, so it doesn't matter which one you take the x. The other one must be x plus s. So suppose I give you a, say in a department store near Christmas, you have many of these boxes, and you want to buy one for your son or your nephew. And you say that, well, nephew, don't bother me. Just go and play with it and tell me you can find out the secret S, this n-bit string. You can imagine that this n is a large number, say 100. Now, if you use a formal mathematical framework, you can show that any classical way of doing it will need exponentially many queries. Because if you don't see, if you don't input enough of the inputs, then you'll never get a collision. And if you don't see any collision, then it just looks like to be a one-to-one function, a random one-to-one function, and you have no hint on where the secret lies. Only when you get 2 input getting mapped into the same output, you can take their exclusive OR and get the secret S. Okay, so you can prove this mathematically very easily. And now, unfortunately, your nephew is a quantum physicist, very, very good at HKUST. And his father teaches here and had a quantum lab, an optical lab in the basement. So let me show you how your nephew can use the optical lab in order to solve this problem. Okay, this is the standard, the canonical diagram. If you have a light source, which is just one wavelength, a monochromatic light source, and you let it pass through a screen at periodic intervals. And now you put a second screen, and you're going to see the patterns coming through the different holes on the first wall. They would interfere with each other, and that produces this pattern. So there are some particularly bright spots, and there are some very dark spots because the light wave would interfere. And of course, the X-ray crystallography is basically if you replace a screen by a crystal, and the atoms in the crystal will diffract this wave, and you will likewise you will see some patterns on it. And so let's imagine creating a crystal. So actually, let's imagine we can grow an n-dimensional crystal. And so there are exactly 2 to the n vertices. And let's imagine each vertex is capable of becoming the source to produce, to get the wave to continue to the second screen. And let's design the light source to be of this particular form. And this light source, the design, will, with the help of the black box. So the design of this interference will utilize the black box together with the secret. And that's why eventually we can decode the secret from it. And now, if you look at any of the vertex x, so this x is going to be specified by an n-bit string. And let's look at the second screen, which is constructed to be a two-dimensional screen. And on each axis, y and z, there's going to be, so it's going to be a discrete screen. So essentially, we are going to divide the intervals into 2 to the n equally spaced, more conceptually, points on both the horizontal and the vertical direction. So the wave that propagates from starting from x is going to reach the 2 to the n points on one vertical line. And this line is, the second coordinate is fixed by the value of f of x. So each vertex is going to propagate to one horizontal line with the distance specified by the output of the one-wave function. And now you can see that typically the points, the waves coming from different vertices, they will not interfere with each other because they are going to be mapped, because the action of the black box, f of x, will take them to different lines, so they will not interfere. The only time they collide is when you have the pair of x and x plus s. These two vertices, they are going to be mapped into the same vertical line. And therefore, on that 2 to the n points, they will interfere with each other. So essentially, we are going to have design a wave which essentially has a uniform amplitude, but its signs depending on a little bit on the first coordinate and the vertex. So let's not go into the great detail. Suffice to say that the pair of vertices x and x plus s, when they go to the vertical line and they interfere, then suddenly you see that originally the 2 to the n bright points, suddenly because of the interference, half of the points will become dark. And the remaining points will become 4 times as bright. Okay, so the magic, the great thing is that the interference condition for having the bright spot relates the secret s and the first coordinate on the bright spot with the algebraic linear relation that s dot y. So these are 2 n-bit strings. You take their inner product modulo 2. It's going to be even. So that is one linear equation on the secret s. And so therefore, in principle, if you have enough independent equations, you can decipher what s is. So you don't need too many. You just need n minus 1 of them. Then you will be able to, independent ones, then you'll be able to calculate what this s is. And so now you see that, unfortunately, the crystal is exponential in terms of its size. It's an n-dimensional crystal, 2 to the n vertices. So there's no way you can do any, even if you can create the artificial amplitude, you will not be able to have a physical room large enough to hold it. And so now here comes the magic of the simulation, namely that you don't need to have 2 to the n, you don't need to have the whole screen to decipher s. You only need to know n minus 1 independent. So if you take 2n random bright spots, they are surely going to be independent. I mean, there are enough independence. And so the trick is that, can you get 2n bright spots? And so now, that is where dimming the light helps you. You can imagine that this whole interference argument is true not for the ordinary optical wave and not only for the X-ray in normal strength, but theoretically, if it goes dimmer and dimmer until only one photon would go through the hypothetical crystals, you will be able to see where the bright spot is. And so if you have a way to do the simulation of this experiment of one photon diffraction efficiently, then you have solved the problem. And that's where the magic of quantum algorithm comes in that you need a quantum computer because this is a quantum event. I mean, it's not a classical optical experiment. You need a quantum computer. And the good thing is that it's simple enough that if you do have a quantum algorithm, you can implement everything with just a linear number of bits. So that is Simon's big contribution. And this is not a toy problem. In fact, I think the most important showcase result in quantum computing, namely Peter Shor's algorithm of factoring large integers, is employing a similar approach. So instead of the Fourier transform on the Boolean cube, he would need to have a more sophisticated way to do the Fourier transform over integer points, but essentially, so you have just witnessed the complete secret of how quantum power is illustrated in its full strength. So, as we said, that we think the great science often happens when the scientific theories interact and new technology becomes available. And so quantum computing is in this really happy situation. And if you really think about it, quantum computing, this model, is the really only challenger to Turing machine model for 80 years. And actually, properly speaking, this really involves a reopening of the famous case of what computation is, because we had thought that the Turing machine is all there is to it, but actually there are alternative ways of doing it, and actually the quantum logic is essentially, I think it's really opaque to most people who are not quantum physicists, and so it's a revolution in that sense. It's a completely different way of doing computation, and the second thing is that fortuitously, that the classical line, the Turing machine model, is finally coming to a certain stage. And for the last 20 years, the computing industry and the computer science really is obeys someone called the Moore's law, so that everything doubles in 18 months, the speed, the memory size, and so on. And those kind of super efficient progress along the existing way of doing it is really coming to an end. And I think that the best estimate would be certainly 5 to 10 years. We'll really have to do something much more innovative than just ask Intel to improve how to make the edge in the silicon to be even closer and closer together. And mainly because the quantum effect is coming to interfere with the entire process. So I think that everybody in computer science knows that one has to deal with the quantum effect. And there are several different ways of dealing with it. And quantum computing offers a particularly daring one. It's namely saying that let's not regard quantum effect as a foe. Let's regard quantum effect as a friend. And maybe quantum computing can really help us. And for many years, people believe that quantum computing is a pie in the sky. But I think that is coming sooner than you think. One day it's going to land on your desktop. And let me tell you my reason for optimism. The first one, this is a scientific trend, in the sense that exploring smaller and smaller scale, the material and the phenomena seems to be the common focus of physicists, chemists, biologists. They all would like to be able to control, to make things smaller, and that they can use. And I think there's no better vehicle than quantum computing, even just from that point of view, to help us focus on how to be able to make devices to control those nano subjects in all its quantum mechanical glory. And the second is that its importance is recognized. So the money is there. In other words, it's recognized by funding agencies and now even companies. You can see that IBM, Microsoft, Google, they all have quantum groups. And IBM and now Google have actually experimental groups doing it. And I think they are serious enough to hire a whole group of physicists headed by John Martinez to make a serious effort on building quantum computers. And thirdly, the work not only have good scientific funding support, but this kind of line of work is now recognized by the physics community. And in particular, I think the Nobel Prize of a few years ago by Harosh and Wannan, and is particularly noted for their contributions to making it possible to do the current quantum computing, quantum processing. And together with that, magazines like Nature Science, you can see that there are a lot of frequent articles about quantum computing. And so what is good is that this creates a career path for young talents. If your work is recognized in the scientific community, you can make a career out of it, then there will be more talented people go in it. Not only young scientists, as we'll see a little bit later on, you can see there are really established, famous scientists who are working in quantum information processing. And finally, the last 20 years, there's marvelous technical progress that have been made. 20 years ago, people were extremely skeptical, even on principle ground, saying that there are problems that cannot be solved just from a scientific point of view. But one by one, I think that right now, no one really is saying that there are some intrinsic reason why it's not possible to do quantum computing. And as a exhibit for the importance of quantum computing recognized, you can see that starting from 15 years ago, there are major centers, very substantial size. Many of them have dozens of professors established, solely devoted to doing quantum information. And particularly the largest one, it's between NIST and University of Maryland. and including even people like Nobel laureate Phillips, and Harvard, MIT, the Center for Cold Atoms, and involves the work of Nobel laureate Ketterle. In Canada, Perimeter Institute, Waterloo, is supported by the government and also by industries. In Singapore, just a few hours away, they have very high profile, and they did extremely well. And there are centers in Europe, Max Planck, and others. And even in China, I think that people are starting to build quantum computing centers. And quantum communication centers have been around in China, but quantum computing, I think they are starting to do it. And the most encouraging of all, I can see that aside from all these mainstream academic institutions that want to build quantum computers in the classical, in the standard, in the very rigorous, systematic way, they are also wild thinking. There's a company called D-Wave, which produces quantum machine, and they sold a few of these machines. I think UCLA had one, and Google also had one. And now Google is serious enough to hire John Martinez to spearhead their effort. And I read in some interview that Martinez thought that they would be able to get something, a prototype in 5 years or so, based on the superconducting technology. And now I'm going to do a little bit advertisement for myself. At Tsinghua University, I started building a quantum computing center 5 years ago. And we get very good support from the government and the university. Even though at that time, I think that most people in China, they believe that quantum computing is just light years away. But we managed to convince some people to let us get a good start. And I think 5 years later, I think that looked like to be a very good move. And the basic idea is that we want to work on a quantum network and a quantum computer. Basically, these two things are very much related because you build the classical large computer by building small computation nodes, devices, and you connect them with networks. And it's the same thing that there's a well-defined theory in quantum computing. How do you connect small quantum computing devices, a few quantum bits, and you can use quantum network in order to hook them up together and build it upscale. So that's our goal. And we actually work on several different technologies. One is called the ion trap, which is the most mature technology, and we are also have built a lab on superconducting bits, and it's in the running. And but the most important, the bet that I will put my money on is the newest thinking in quantum computing, namely to use diamond, just the ordinary diamond, as the medium to be the storage and the processor for quantum computing. And there was a really nice article a couple years ago in Scientific American. It's called The Diamond Age of Spintronics. So they argue that human civilization went through stages. You first have the Stone Age, and then you have the Bronze Age, and you have the Iron Age, and you have the microelectronic age. And the authors believe that at least in terms of computing and information processing, the next big age is going to be the Diamond Age. And it's called spintronics because they need to use all those little spins, the nuclear spins, in order to implement all sorts of computing states and bits. And in Tsinghua University, we have a group headed by Professor Lu Mingduan, who is a long-term visitor in our center, but his regular job is in University of Michigan. And they published a paper a year and a half ago in Nature, in which they show that how can you build a robust set of universal gates on diamonds so that it can serve as a basis for the small computing device. And the science is that in a diamond, without any deficiency, the diamond would be a very regular structure, and every of these items would be nitrogen items. But either by accident, or better still, if you plant it so that you can put in a nitrogen atom into the mist and to knock out one of the carbon atoms. And now, this is just a rarity. It's just sometimes you have some undesirable thing, carbon-13, but it's harmless. And so there's a way that one can produce diamonds so that it be suitable for you to inject nitrogen into it in a systematic way, so that you can create lots and lots of quantum bits that you can use. And now the good thing about the diamond is that it works in room temperature, and it has a structure very similar to the silicon case that as we are very familiar with, and we know that the silicon is often associated with the possibility for you to scale up your invention and your little computer into a big one. So the diamond-based computer has this lower for it. And, but this really involves very detailed process of combining physics and engineering. So in our lab, we have built a clean room, and we have built up fabrication facility for doing this kind of fabrication. And you have to be able to do your own, because you cannot buy this sort of thing. You have to do it in-house. So this is sort of what it looks like. I think the little holes that will hold the diamonds atoms, so that you will, so 2 microns in this, and you have on each of these holes, you have to cap it with some sort of lid. And now in our lab, we are building a wall of a certain height, a few microns in height, and so that the atoms are going to be, the nitrogens are going to be implanted. So that, in other words, we'll have this diamond ring, and to be filled with qubits, and then later on you can use light in order to do interactions among the atoms. So now this you cannot see very well. Basically, it's just a few hundred of these basic units. They can be laid out on a wafer and to integrate it. So I'm going to conclude. I just reiterate my point that the scientific theory, when the disciplines interact, and when these get into the most fundamental and basic stage, that is when opportunities are ripe for people who like adventures, who want to go at the ground floor, and usually even do relatively simple things would eventually turn out to be very important and for the subject. And I think that quantum computing is still in this situation where it has developed so that it's not a wild goose guess. It's really safe to get in. But on the other hand, it's early enough that you can make big discoveries. And to end the whole thing, let me just go back to the very beginning. I skipped over the question, what is a great science? And I refused to answer it, but I think that I like to face it a little bit toward the end. So even if you disagree with me, fine. Firstly, it must have deep impact. And quantum computing is important. Actually, I would argue it's not for breaking the integer codes. I would argue it really because it focuses the energy into a particular application where the extreme care and technical and scientific knowledge would be needed in order to do it. And I think that there will be many, many byproducts and applications. And in addition, it has some lore in terms of science. And because in quantum physics, we know that even if you have the quantum equations, you don't know how to solve them. And you don't know how to make predictions. If I give you two theories of superconductivity at room temperature, you might have difficulty of saying who is right, because you cannot really produce answers from the theories. And if you want to simulate it with the classical existing electronic computer, it's way beyond your ability. You cannot never do it. However, if you do quantum simulation, in principle, you can do it. And actually, even before you can have the full general purpose quantum computer, there is a quantum simulation. It's an idea that if you have another either artificial or natural system which are very similar to this quantum system you are interested in, you can manipulate these more friendly systems so that you can simulate the tough systems that you don't know how to get answers of. And so, so this would also have great impact on the development of physics. And lastly, I would say that I really think something called great science only when you provide some imagination, and so that you can attract even very young school children to it. And for the case of the quantum technology, I would just use the following metaphor: that we know the language of quantum mechanics for over 100 years, and we know actually the precise formula for many things, except that we don't have anyone to talk to, because we don't know how to communicate. And now suddenly, it's just like that in deep South Pacific, there's an island of natives who can speak a certain language that's very, very hard and difficult. But we learned the language, but we couldn't get there to talk to them. And if you suddenly can go to their village and talk to them, I think that's the dream of every science fiction. I think in the quantum case, it's something that's right here. We now, finally, after all the big inventions, many Nobel Prize-winning things like laser, like electromagnetic dynamic trap, and suddenly it gave us all the tools to manipulate individual items and the electrons. And so it's like we can talk to the native. And not only talk to them, we can instruct them to do things. So how much wonderful can it get? So with this, I close my case.